I'm Pat Dugas, and this screencast is about rational exponents, being able to write and simplify expressions and convert from between the rational exponent form and the radical form, which we've covered in previous screencasts. So let's begin with a definition. If we have a base b raised to the 1 over n power for any real number b and positive integer n, then b to the 1 over n power is equal to the nth root of b. And that is except for b less than 0 and for even n's, because even n's could result in more than one answer for that. When b is less than 0 and n is even, then a complex root may exist. So for example, 27 to the 1/3 power is equivalent through this concept of the third root of 27. Or the third root of 27 is 3 because 3 to the third power is 27. In a similar way, if we have negative 16, and this is that case where the base is less than 0, if we have negative 16 raised to the 1/2 power, we get the square root of negative 16, or the second root of negative 16, and that is 4i, an imaginary number. Now we're going to expand that actually a little bit, not just 1 over n, b raised to the m over n, where m and n are integers, is equal to the nth root of b to the m power. Okay, and this allows us to go, both of these things allow us to go between exponential form, which is the form you see on the left, where the power and root are exponents, and radical form. And you can see that the n is the index, or root, and the m is the power to which the base is being raised. Let's look at some examples of translating between radical and exponential forms. So let's take a to the 1/7 power and write it in radical form. Well, the 7, the denominator, is the index or root, and so this becomes the 7th root of a to the 1st. The square root of w in exponential form is like the second root of w, or w to the 1/2. You remember in algebra, if there is no number in that root, that is a 2. And the last example is that b to the m over n form. So x to the 2 over 3, or x to the 2/3 in radical form, becomes the third root, because the index is the root, of x to the second power. The n, or the root, is the 3, and the m is the numerator of the power. Let's evaluate some expressions that don't necessarily involve variables. If we have 49 to the negative 1/2 power and we need to evaluate that, there's actually a couple of ways to do this, and we're going to look at both of them. So one way is to just take that number 49, and since it's to the negative 1/2 power, we know by our definitions, that's the same as 1 over 49 to the 1/2 power. We really want to get rid of the negative exponent. So you will recall from previous screencasts that a power to a negative power is the same as that power being in the denominator. So it's 1 over 49 to the 1/2 power. Well, 1 over 49 to the 1/2 power can be written in radical form as 1 over the square root of 49, which is 1 over the square root of 7 squared, or 1 over 7. Some people might skip directly to that step, recognizing that the square root of 49 is 7. Another way of doing this is to recognize that 49 is already a perfect square in the beginning, and rewrite that 49 as 7 squared. And then we take 7 squared raised to the negative 1/2 power, and that becomes 7 to the minus 1, because you will recall if we raise a power to a power, then we're going to multiply the exponent. So 2 times negative 1/2 becomes negative 1, and 7 to the negative 1 power, based on our negative exponent rule, is the same as 1 over 7. Either way, you're going to get to the same answer, so it's comforting to know that there are multiple ways to go about this. Let's look at another example. Let's say we have 32 raised to the 2/5 power. This is that m over n example. Okay, so method 1 would be just take that 32 to the 2/5, and we rewrite that as 32 to the second power to the 1/5, because 2 over 5 can be written as 2 times 1/5. And so that's just 32 squared raised to the 1/5 power. Well, this can be rewritten directly into radical form as the fifth root of 32 to the second power. Well, 32 is 2 to the fifth power. You might have even recognized that originally. That'll come into method 2. 32 is 2 to the fifth power. And remember, if we're going to try to simplify things that have radicals, we're looking for things that are already raised to that root power. 2 to the fifth squared can be written as 2 to the fifth times 2 to the fifth. Okay, and so now that fifth root can come into play in an inverse operation with 2 to the fifth, and that becomes 2 times 2, or 4. So 32 to the 2/5 power actually winds up being 4. It's interesting to note you can also evaluate these on your calculator because these rational exponents work just like regular exponents on your calculator, whatever type of calculator you're using. So let's look at the second method. You might have already realized in the beginning, if you're familiar with your powers of 2, that 32 is equivalent to 2 to the fifth. That works out very nicely because we have 2 to the fifth raised to the 2/5 power. And so when we take 2 to the fifth and raise it to the 2/5 power, we're multiplying those powers, and we get 2 to the second power, which is 4. Let's work on simplifying expressions that involve rational exponents. Suppose we have an expression y to the 1/7 times y to the 4/7. We can actually directly multiply these powers, and when we're multiplying two terms with the same base, we can then add those powers. So this becomes y to the 1/7 times y to the 4/7 equals y to the 1/7 plus 4/7. And so that actually equals y to the 5/7. We just add those exponents. So let's say we have the sixth root of 16 over the third or cube root of 2. Well, we can rewrite the sixth root of 16 as 2 to the 4th, all raised to the 1/6 power, because 16 is the same as 2 to the 4th. And then we have 2 to 1/3 power is the exponential version of the cube root of, or third root of 2. Because we have the same base here, now we do need to simplify we need to work out the numerator first. 2 to the 4th raised to the 1/6 power becomes 2 to the 4th times 1/6. So that becomes 4 over 6, 2 to the 4/6, which is the same as 2 to the 2/3. The denominator is already 2 to the 1/3, so I have 2 to the 2/3 divided by 2 to the 1/3. Well, because I have the same base, I have a quotient of powers, and I can subtract those powers. So it becomes 2 to the 2/3 minus 1/3, or 2 to the 1/3, or just the cube root of 2. So let's do another one here. The sixth root of the quantity 4x to the 4th. So let's rewrite these as rational exponents. Rational exponents have the advantage of being able to use our laws of exponents, and sometimes it's easier to take them out in that form instead of a radical form. So this is the same thing as 4x to the 4th, all raised to the 1/6 power. And so what we're going to do now is take the 4 and turn it into a power of 2. So 4 is the same as 2 squared. X to the 4th is the same as x squared squared. And all of that is equivalent to 4x to the 4th raised to the 1/6 power. We're going to take each of those terms. That becomes 2 to the second raised to the 1/6 power. So we're going to multiply these exponents. And then we have x squared to the second power, also raised to the 1/6 power. When we finish that multiplication, we get 2 to the 2 over 6, which is 2 to the 1/3. And then we get x squared to the 1/3 power, because 2 over 6 is the same as 1/3. And then we're going to go ahead and put them back into radical form. Since the original problem was in radical form, we're turning this back into radical form. So that becomes 2 to the 1/3 is the cube root of 2, and x squared to the 1/3 is the cube root of x squared, or also x to the 2/3. And we'll finish off with a more complicated expression that's going to involve conjugates. Y to the 1/2 plus 1 divided by y to the 1/2 minus 1. What we're going to do here is use the conjugate of, we have a radical in the denominator essentially, because y to the 1/2 is a radical. So we're going to find the conjugate of y to the 1/2 minus 1. And the conjugate of y to the 1/2 minus 1 is y to the 1/2 plus 1. So if we multiply the numerator and the denominator by y to the 1/2 plus 1 over y to the 1/2 plus 1, we are multiplying by 1. So now what we have to do to simplify this is distribute the numerator and the denominator. Okay, when we distribute the numerator, we get y to the 1/2 times y to the 1/2, which is y. And then we get y to the 1/2 times 1 plus 1 times y to the 1/2. So that's where our 2y to the 1/2s come into play. And then we get 1 times 1, which is 1. So the numerator binomial times binomial simplifies down to this. The denominator, because it's a difference of two binomials, is the middle terms are going to cancel out. So we get y to the 1/2 times y to the 1/2, which is y. The middle terms, we have y to the 1/2 times 1 minus y to the 1/2 times 1. So the middle terms cancel out. And then we have minus 1 times 1, which is -1. And that is all we can do with this. This is in simplest form. So this screencast has been about an introduction to rational expressions, which is another way of writing radical expressions, and often is easier to work with because our laws of exponents apply directly to them.